Can everyone hear me? All right, cool. So, you guys having an exam this week. You still have homework due on Thursday that was posted on Friday after homework 7 was due. Um, the reason that I make homeworks still due when you guys have exams is because this material is stuff that you need to know for your exam. So it's going to involve problems that you should probably practice before taking your exam. So that's why the homework is still due on Thursday. We're a little bit behind on lessons and lectures and like things I want to get through. Um, and there's like a university policy of like when I can give the last exam, like before the final. So I can't move exam 3 back. Um, so we do need to have class on Thursday just to keep up or catch up with all the other lectures. So because we're gonna still have class on Thursday, I have extended the amount of time that you have to take exam two. So instead of it being 24 hours like the first exam was, you now have 48 hours. So you have Thursday and Friday to do it. If you don't want to work on Friday and just want to get it all done on Thursday, that's fine. Just like turn it in, just turn it in before 11:59 on Friday. I don't accept late work. Um, and yeah, there are problems since we are working with real life problems, not a lot of numbers work nicely that you can just like easily divide in your head. So I will be allowing you guys to have a 4-function calculator for this exam. I'll be sending you a link to Desmos calculator, um, just so you're not tempted to like look at your phone and do stuff like that, and you guys can be as honest as possible. Um, practice to exam has been posted and solutions were posted for it as well. Again, the practice exams are a really close comparison of what the actual exam is going to be like. So if you look at the practice exam, the first few questions are, what's this mean? What is this formula? So kind of like vocab and questions, not questions, formulas. So know all of those. I always like make a, what is it called? Like a study sheet with all of mine when I study for exams. Um, let's see. Homework is still due on Thursday. Exam opens Thursday to Friday evening. Practice exams open. We'll still have class on Thursday. I think that's all announcements that I have. Does anyone have any questions about exam two or homework at all right now? Oh, my nose. I'll give you a second if that's a really good question, Ronald. I've updated. Ooh, this is another good thing. Thank you. Um, I've updated the syllabus to reflect that we're having class, and it has all of the sections listed. So I think it's 1.5 to 2.7. Obviously, we didn't do every whatchamacallit section in between that. Like I don't think we covered 1.6, but it's explicitly laid out in the syllabus. So all of chapter one, except for like 1.3, 1.4, because that was on the first exam, and all of chapter two. And then your next exam will be chapter 3 and chapter 4. Keeps it nice and easy if you do it chapter by chapter. Okay. Oh, that's a really good question. I now remember what the other thing was. Let me move our to-do list down. Tomorrow evening, right? Usually on the Wednesday before or the day before our exams, we have review sessions. So I have a class that goes until 5:10. So from like 4 to 5:10, I have class. What else do I have class tomorrow? So I usually like to have review sessions in the evening, so any time after like 5:30. So if you would like to attend the review session, what time tomorrow evening works best for you all? You just like throw that in the chat. Um, a lot of you guys said 7 or 8 last time, and then like 3 people showed up. which shout out to those 3 people. I was making chicken nuggets. 7 works. Okay, 7's a really good time. Is anyone opposed to 7? Okay, Kara says 7. 7. All right. Speak now or forever hold your peace. Okay, 7 it is. What's tomorrow? The 24th? I have a meeting. Okay. I have a meeting tonight at 8, and I had to remember that. Okay. So review session tomorrow. It's gonna be here. I'm putting this on my phone so I don't forget about it. You guys are just like sitting here being like, where is she? Doo-doo-doo. 7 p.m. Okay. Review session. And remember, you guys need to come with questions. It's not something that I am going to like bring questions to. This is stuff that you guys are be asking me, and we can go over it. We can go over the practice exam in more detail. We can go over if I change this in the practice exam, how would I do that? Can we go over this homework problem and stuff like that? All right. So come with questions. I will come with answers. All right. Okay, cool. I haven't finished grading homework 7 yet. I've done the first few. My computer like was not having it this morning. But a common thing that I was seeing a lot, because I don't want you guys to like miss out on this on your exam if I ask similar questions. You had homework problems in the written portion that were like, what is the y-intercept? What is the slope? And then you would just give me the equation of the line in y-intercept form, which is great. I'm really glad that you know how to do that. But like, that's like, hey, I don't know an example of that, but like, you're not giving me what I asked for. You're giving me something else and the answer's in there. I want to make sure that you understand looking at that equation. Oh, this is the slope. This is the y-intercept. I can't tell that if you just give me the equation of the line when I ask for slope intercept and intercept. So I like couldn't really give you full points because I don't know if you're like, oh, what if you tell me the y-intercept is the slope and the slope is a y-intercept? I can't make these assumptions from your answers because that one would be unfair to you. And 2, it's not even the answer. Does that make sense? Like answer the question. What is the question asking for? And make sure that it's explicitly stated in your answer. Okay. 56B. I'm pretty sure there was no graph because 56, let me go. What was 56? 56A was to find the slope of the line, and B was to find the X and Y intercept. So I think part C, I don't know what part C was for 56 because that wasn't on, I didn't feel like I couldn't do it. So I don't think there was supposed to be a graph. I don't have the textbook in front of me, but unsure. Right. Some of you guys just like, it's not just Ronald, just like skip parts of the question and I get confused. Like, okay, did you not want points for that? That makes me sad because then I can't give you points for that. Okay, cool. Does anyone have any overall questions about homework 7? Remember you can still turn in homework 7 by Thursday and you'll just get a 10% point, but it needs to be done before the exam that covers that material. So that's my stipulation. You can turn it in for a very small late deduction fee, whatever. It just needs to be turned in by the exam. Are you asking about for the exam or for homework? Homework. It would be nice if you guys did write it. Some of the word problems are like really, really long. Like I think the windmill one was like a paragraph. that's pretty much fine. But like, yeah, it's a whole paragraph and it's a lot. I usually just kind of like, if you guys, like, if it's like, find the line parallel to this line, and then you guys just like show some work instead of writing the question. I get confused. It's more of a preference. I don't take out points if you don't write out the whole problem. But if it's a whole paragraph, when I write my homework down, this is just a preference for me. I kind of write like a, what is it called? A summary of the problem, but you don't have to. For your exam though, I would really like for majority of the problems to be written down. What is that, the online book, Griffin? Obviously, right? Okay. If you have physical books, it would show you pictures. That's interesting. Okay, I've never heard of that problem before. Okay. That I would say try a different browser, or maybe like go in incognito mode. Oh yeah, might have a lot of pop-ups. Okay, we need to move on. So we're gonna do 3.1 today, and we're gonna do 3.2. Okay. So we kind of started 3.1 last week, right? So we've been talking about lines. What is this line in here? Straight. And when we talk about a line, I'm literally talking about like a straight line. If it has any curve to it, that is a curve. So we have stepped away from lines. We're done with them. And now we're going to talk about a specific type of curve, an exponential growth and decay. So modeling different real world examples. So right, when we talk about growth, we can talk about population. We can talk about cell growth. Also, exponential growth can be modeled with, what's it called? Has anyone's ever heard an SIR model? Susceptible, infected, and recovered. About like bacteria disbursement and getting people sick and stuff like that. Decay, we usually can also talk about population, like people moving away at an exponential rate. I like to think of them moving away, not them dying. And then radioactive material is your most common exponential decay. If you've ever heard of half-life of a material, right? So then we have the model for exponential growth, right? So whole chapter is about growth and decay, and now we're just focusing on growth, and there is a difference. So exponential growth is modeled by a function of the form f of x equals c a to the x. So a is the base here, right? And that's the only thing raised to the x. C is not raised to the x. We talked about that distinction when we talked about exponents in, I think, like chapter B. And in this case, we have that a is larger than 1. It's not equal to 1. There would be no growth if it was. And we'll talk about what it means when a is less than 1 in a little bit. So x is going to be the number of time periods. We can either have 1 hour, 1 second, 1 day. I could have 3 months as a time period, and so on. A is called our growth factor. And then C is our initial value, which we can see if I put my initial values like f of 0. Oh, look, I wrote it over here. Anything to the 0 we know is 1, so I just had C left over, okay? And our general shape is like this kind of guy. Whee! And this also kind of keeps going back and back. We usually don't think of time as a negative though. Okay, so we did a few short problems of finding the equation. So if a bacterial infection starts at 100 bacteria, that's our initial value, 100, and it triples every hour. So triples every hour tells me that A is going to equal 3. And since I start with 100 bacteria, that means C is going to be 100. This also tells me a little something extra every hour. That tells me that X is in increments of 1 hour. So if it tells me what's happening 30 minutes later, I have to adjust that to talk about hours, okay? So then we did one, oh yeah, and that was our final equation, right? So then we were given that a pond was stocked with 5,800 fish and each year the fish population is multiplied by a factor of 1.2. That one was a little bit more explicit about what our growth factor is. It literally says by a factor of 1.2. And the word factor was used very intentionally here. So that means that my growth factor, I don't have to think about double, triple, quadruple, something like that. Just given to me is 1.2. And I'm given my initial value. So I put those both in the equation that we talked about above. And there we go. So any questions? I kind of went through that a little fast, but I'm just kind of reviewing. Any questions about creating a model from so far? Okay. Am I recording? Yes. Cool. So then we talked about very, very quickly, I like kind of got ahead of myself. What if I'm not always given something very nicely like, oh, it triples every hour and it's a factor of 1.2? Like in the real world, if I am doing some fun biology research, I'm not gonna like the bacteria aren't gonna be holding up a little sign that says, I'm gonna triple every hour. Like, how am I going to figure that out? So we have this fun little equation, right? So the growth factor A is the number by which the population is multiplied every time period. So every hour, year, whatever. So increasing by x by one time period, we'll get f of x plus a, sorry, f of x plus 1 equals a times f of x, right? And we kind of saw that when, sorry, I need to scroll. I was seeing if something triples every hour. So if I started at 100, after the first hour, I'd have 300. It triples, so it's 3 times as much. After 2 hours, it triples from that beginning hour. So again, yeah, I rushed it a lot last week, and I'm sorry about that. I was so excited about it. Exponentials and logarithms, we'll talk about logarithms later, are my favorite things in this course. And then so on. So that's where we get this phrase from, right? Every one more time increment, it's going to be that much time, that a times what it was in the beginning of that time period, right? Let me erase this teacher question from our exit slip. You guys told me some okay jokes. A lot of people told me about the chicken crossing the road. What, I'm just trying to like look at them today to see if I had my favorite. Someone said, is mayonnaise an instrument, which was really funny. And then a lot of people asked me, why did the chicken cross the road? I think I had that like 3 times. That was really funny. All right, cool. So if I'm not given A, but I'm given these time period, like if I'm given like, this is what's happening at hour 1, and then this is what's happening at hour 2, I can then find my growth factor. And that's because of exponential laws and rules that we talked about early in the semester. So I got these 2 parts of my division right here from just the equation of exponential growth, right? So C over C, those cancel out, and then I'm left with a to the x plus 1 over a to the x. Well, I know that I can make a to the x as exponents are added, so I can make it into something where the bases are multiplied and it's the same base. So I'm kind of like decomposing it. So I'm left with a to the x times a to the 1. Then a to the x over a to the x cancels out, and I'm just left with a to the 1, which is just a. So that's where that comes from. And it has to, and it's very intentional as to why it needs to be the very next time period. You can't use this exactly when we're talking about, okay, if I'm doing increments of like 1 hour, I'm like, okay, at 1 hour, it's this much, at 5 hours, this much. I can't divide them if I'm talking about, that's too far away. I hope that makes sense. Okay. So this is a really cool gift that we were given, but we can't use it lightly. All right, so let's use it in our problem. A chinchilla farm starts with 20 chinchillas. Okay, so C equals 20, right? I'm going to start with 20 chinchillas. That's my initial value. And after 3 years, there are 128 chinchillas. Wild. Has anyone ever had a chinchilla? My friend in high school did, and they take little dust baths, and I think it's really cute. So assume that the number of chinchillas grows exponentially. Find the 3-year growth factor. So, like I said, like 5 seconds ago, if I'm using my time increment of 1 year, I can't go 4 years later and use this above. But now I'm told this is the 3-year growth factor. So that means that one time increment is 3 years. So 3 years later, I can divide these, right? So it'd be like f of 0 equals 20, and f of 1, one time period, is 128. Is that clear? That I'm finding the 3-year growth factor. So that means that my time increment, because remember we talked about x being the number of time periods that have passed, one time period here is 3 years. So that would mean f of 0 is 20, right? I start with 20, but after one time increment, I have 128. Is that clear to everybody? Okay, cool. So I'm going to pull up this thing, x plus 1, and f of x. So in this case, I can just use f of 1 over f of 0. Would you guys agree? Yeah. So use 128 over 20. Oh, I feel like I get like 5 something, but that doesn't sound right. 6.4. Oops. And there's no units on this, by the way. So 6.4 is my 3-year growth factor. So we can even just nicely write down here, A is 6.4. Okay. So any questions about how to use this little formula to find A so far? And also, no, because we're not going to use, it's okay for a growth factor to be a decimal. I understand that working with chinchillas, and we cannot have a percent of a chinchilla or a decimal of a chinchilla, but rounding this number right now and just in future uses is going to really, really hurt your number. That is a really good question, Griffin. No. So we're finding the 3-year growth factor. So that means one time increment is 3 years. Right. So up here in our definition of exponential growth, x is the number of time periods. So when I'm told to find, to find the 3-year growth factor, I'm in turn told that the time period is, one time period is 3 years. So making after 3 years, that would tell me one time increment. Yeah. So I was trying to like really stress that. That was a really good question. Okay, awesome. So how are we feeling so far about exponential growth models? Are we feeling thumbs up, thumbs sideways, or thumbs down? Okay, rad. What is this definition? Okay, cool. So, right, this is a little confusing. So I see a lot of the ups, but I was expecting a lot more sides because exponentials are weird. Cool. So we just talked about the growth factor. So that's A. Now we're going to have something called the growth rate, right? So growth rate of a population is the proportion means they're going to be division of the population by which it increases during one time period. All right, so that yields something like this. So we call the growth rate R, has a rate R, and it's going to be f of x plus 1 minus f of x divided by f of x. There we go. So this looks really similar to our growth factor, which was just this part, but now we have this additional minus f of x in the numerator. So growth rate is going to be R. I like to think of it because, well, rate starts with R. And then factor, that'll be A. So the A comes before the R in the word factor, where in the word rate, R becomes before the A. That's how I remember it. Okay. So it's the population, is a proportion of the population by which it increases during one time period. So, right, this is the net change in one time period. You all remember the formula for the net change of something? It's like f of b minus f of a. It's the numerator in this average rate of change equation. So this is the net change in one time period divided by the beginning of that time period. Okay. So let's do some fun problems with it. All right, so 50 rabbits are introduced into a small uninhabited island. They have no predators and food is plentiful. So they can just, nothing's taking them away and nothing is holding them back. So the population grows exponentially, increases 60% each year. So now we're given a percentage. All right, so if I'm increasing 60% per year, would my growth factor be 0.6? What are we thinking? It's 1.6. Ronald, how did you get that? That is true. If it was 0.6, it would be decrease. It would be exponential decay. Yeah, we'd be losing rabbits. Before we move on, I want to show you guys something cool. If I decompose R, so if I get like f of x plus 1 over f of x minus f of x over f of x, do you see, right, that's just from pulling those two fractions apart. Yeah, it's 100% plus 60%. Then what's this guy right here? What's f of x plus 1 divided by f of x? What's that? It's our growth factor. So it's going to be a minus 1. So just from the definition of R, careful, not the rate, it's the growth. It's the factor. We're given that R equals a minus 1. Oh, sorry. Which also implies that A equals R plus 1. So if I'm given the growth factor and the growth rate or the growth rate, I can find the other one just by adding, subtracting 1. Since I'm told that I'm growing exponentially, that tells me that A needs to be greater than 1. So that automatically tells me that that 0.6 is not A, and that it's going to be our growth rate. So I'm told basically in words that R is 0.6. From the definition of R, I know that A is going to be 0.6 plus 1. So it's 1.6. Another way is you could have just set our first equation definition for R. Let me put this in a box. This deserves to be in a box. And set that equal to 0.6 and solve using like CA of X and stuff like that. But that's kind of what we did to get these two. Okay, is everyone clear about how I got A is equal to 1.6? Because that was really fast and I want to make sure I can go over it again. Okay. Remember when we were talking about interest rates? We were given a percentage. If I'm given a percentage of something is growing 60% a year, that is a really key indicator that that is going to be R. That is our growth rate. If it's a percent. If I'm given by a factor of something, that's going to be our growth factor. So that percent right here, rates are presented in percents. Okay. So that is a really good, this percent sign is a really good indicator that it's going to be R, and that'll help me find A. Okay. So what is, my population grows exponentially. So it's like P of X equals C A to the X. I found A. What's C? What do you guys think C is? It's 50, right? There's no number, but it tells us in words, 50. Great. So now I have the two key things that I need for my model. So I have 50, 1.6 to the X. I like to write in parentheses so it's clear that 1.6 is the only thing raised to the X and not the 50. Okay. So how many rabbits are there after 8 years? How can I find that out? X equals 8. Let's double check. And the way to double check that is it tells me after X years. So, and it's told each year. So I don't have to do anything weird with changing my times. So I'm just going to do P of 8, and that's going to be 50 to the 1.6 raised to the 8. This is why you guys get calculators, because I don't know what that is. Times 50, and I should get 2,147.48, and I'm just going to round that up to 148 rabbits. Okay. Actually, I'm going to round it down. I'm not too strict on rounding. As long as you're like there and plugging in the numbers, I'm happy. There are some times where you'll be asked why something doesn't work, and one of the answers will be close to making a decimal. All right. So we've talked about the difference between growth rate and growth decay, especially when it's growth rate, it's going to be a percentage. And if it's a growth factor, it definitely has to be greater than 1. So if I'm given a percent that's less than 1, it's definitely not my growth factor because that has to be more than 1 because that's helping us grow. Okay. Any questions about growth rate and growth factor right now? And how do we feel about the problem that we just did? Are we feeling thumbs up, thumbs sideways, thumbs down? How are we feeling? Okay, cool. Maybe there's an SI session tomorrow at 5. Yeah, Johanna also carries those. Okay. Whee. So now let's talk about exponential decay. So exponential decay. This model doesn't look too different. It's still going to be f of x time equals c a to the x, but now a is in between 0, 1, not inclusive. Can anyone tell me why a can't be 1? Yeah, it wouldn't grow or decay. It would just be c the whole time. 1 to any power is just 1, except if it's infinity, then it's undefined, but that's a different thing. So that's why you don't want 1. The reason we don't want negatives at all is because that'll switch. If I like square a negative number, I'll go to positive. But if I cube a negative number, I get a negative. So as time goes on, I switch between being a positive number and a negative number. And that doesn't really work in the case of population, negative cells. That's kind of confusing. So that's why a can't be a negative number, because it doesn't really model a thing in the real world. And it can't be 1 because it won't grow or decay. All right, so the base A is not our growth factor now, it's our decay factor. Right, and so R is not our growth rate anymore, it's our decay rate. C, still our initial value, and so on. All right. Right, so which satisfies R equals A minus 1. So R is going to be negative in this case. I'm decaying. A percentage is going away. Okay. So what kind of shape of a graph do you guys think this is going to look like? Yeah, bud. Not very straight, but starts at the top and goes down, right? So we're going to start up at C and I'm going to decay. And I'm actually not ever going to touch this axis. I'm going to decay, but I'm never going to really, I could hit 0, but not really. Trying to think of what I was going to say. This causes what's something not really important to this class, but if anyone's ever heard of asymptote. No, does it keep going down? Yeah. So it's exponentials are what we call asymptotic. Yeah. Yeah. Okay. Cool. So, let's do a problem. A patient is administered 75 milligrams of therapeutic drug. Like, I don't know, Advil. I don't think the textbook wants to say morphine. It's known that 30% of the drug is expelled from the body each hour. So 30% of the drug. And then I also like to highlight our time period. So each hour, 1 hour is our time period. Okay. Find the exponential decay model for the amount of drug remaining in the patient's body after X hours. Okay. So f of x equals c a to the x. That's still our exponential equation or formula, sorry. Equation. Model. There we go. What is C in this case? Right, 75. Beautiful. And then I'm given 30% of the drug is expelled from the body each hour. How can I use that to find A? And what does that tell me? If 30% is expelled, A is 0.7. Ronald, how did you get that? Right, Jared, I'm going to subtract 1.3 from 1, right? So 30% is expelled, so my decay rate is going to be negative 0.3. 30% is leaving, and I know that, what was my equation? Yeah. A equals R plus 1, so that would give me negative 0.3 plus 1, which is saying 1 minus 0.3, same thing, which is going to be 0.7. Perfect. So that's my A, and there's my C. So f of x equals 75, 0.7 to the x. You can also put the x outside the parentheses. Okay. So I don't know why this got cut off, but we're asked to use the model to predict the amount of drug that remains in the patient's body after 4 hours. This is really actually useful and used in medicine, so you don't hurt your patient and they like unalive. So what do you guys think I should do? Right, I want to plug in 4. So f of 4 equals 75, 0.7 to the 4. It's my handy dandy calculator. 0.7 to the 4 times 75 is going to give me 18.0075, or you can just say 18, that's the same amount of rounding, milligrams, right? Beautiful. How are you feeling about exponential decay so far? Are we feeling thumbs up, thumbs sideways, thumbs down? She's not too different than her friend. All right, cool. So the half-life of radium-226 is 1600 years. A 50-gram sample is placed in an underground disposal facility and monitored. This is actually what they do, which is pretty cool. So I think I forgot something in here. Oh yeah. So I start with 50 grams, and I'm told that its half-life is 1600 years. So half-life tells me a lot of information. Does anyone know what it means for something to have a half-life of so and so many years? It loses half of its mass, right? So if I start with 50 grams after, right, we're finding it for X amount of half-lives, I would only have 25 after the first one. Yep, exactly. And then the next one I would have half again. So f of x equals c in x. My c, we see, is going to be 50, but what's my a? What's my a going to be? If after 1 half-life, it's going to be, yeah, it's going to be 0.5 or 1/2. Either is correct. Great. Because we're using x half-lives. If we're given years, we have to tweak it just a little bit, and we'll learn more about that in a little bit. Right, so I can use f of x equals 50, 0.5x. Beautiful. So if I'm already told half-life, I'm already told, oh, sorry, a lot of information with that. So now we can use the model to predict the amount of radium remaining after 4,000 years. So my model is for half-lives, right? So it was like 50, not 1.2, I don't know where that came from in my head. Oh, 1.5, that's what I wanted, right? To the x, where x is half-lives, not years. It's 100 and, oh, sorry, Anna. Our half-life is 1,600 years. So after 1 half-life, it's been 1,600 years. After 2, it's been 3,200 years, and so on. So how can I find out at 4,000 years how many half-lives have passed? It's kind of like moving in from minutes to hours and stuff like that. Right, exactly, Ronald. 4,000 years over 1,600 years will give me 2.5 half-lives. So you think of like 1 half-life is equal to 1,600 years. So yeah. Okay, so I'm just going to divide, and that's going to tell how many half-lives. So I'm going to go over here and I'm going to plug in 2.5 instead of 4,000. That's why it's really important to check on the units of things. So 0.5 raised to the, oops, how do I delete? Oh, wait, that's what I wanted. 2.5 times 50 is going to give me 8.84 grams. It's kind of a lot. Grams overall, right? So that's how much is going to be left after 4,000 years. Okay. Is everyone clear on that? How are we feeling so far about exponential growth and decay? Because I think we just finished this section. Yeah, we did. Cool. All right. Any questions on this problem? The hard part about this problem was seeing that it was half-life, right? So half-life tells me that most of the time A is going to be 0.5 if my X is measured in half-lives. I'll have to do some adjusting if I'm changing it into years, and we'll talk about that later on. Duke, it's okay. And that's the adjustment that we had to do down here. Okay. It's like if you've ever tried to put in something that only takes quarters and you're planning to put like pennies and dimes and it just spits them back out. That's kind of what would happen here. If I put it in 4,000, I would get something completely different. Okay. So let's move on to, so we're done with this one. Done. 3.2. All right, so it is Tuesday. What day is it? March 23rd. It's Aries season. I think it's spring now. All right, cool. So now we're going to talk about comparing rates. So we talked about a 3-year growth factor when we talked about that rabbit problem. Was that the rabbit problem? And we talked about half-life, where like a half-life was so many years and so on. Because that X is a number of time periods, not the number of hours necessarily. So suppose we want to change the growth factor for an exponential model. So if I have like a Wheatley growth factor is B, and A is the daily growth factor, what should A and B satisfy? So how do you guys think I can take a daily growth factor and a weekly growth factor and compare them to each other? What are some ideas? Well, well, they can't be equal. One's a weekly growth factor, one's a daily growth factor. How can I set them equal to each other? There has to be some other things moving around. I can't just say A equals B. That's not true. 1/7, yeah. So a day is 1/7 of a week. So if I were to look at, right, so let's do W of X equals C B to the X, and then D is going to be like C hat, call him something different, A to the X. So here X is in weeks, and here X is in days, W and D, okay? So if I wanted to find what's happening at day 2, I would just put in 2 right here, right? Into the daily one. I would do like D of 2 equals blah, 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 A to the 2. But what about day 2 if I'm using a weekly rate? A weekly growth factor, excuse me. I would do 2/7, right? So I would do, it wouldn't be 2, it would be 2/7. And since I'm modeling the same thing, these things need to equal, right? Actually, they would have the same initial value, so that C is the same. Because our initial value is the same. So these things have to be equal. Would you all agree? If I'm modeling something using, it's the same thing I'm modeling, so their outputs have to be the same. So if I had like B, so then if I set them equal to each other, I would have like C B to the 2/7 equals CA squared. I would then need to get one in terms of the other. We're modeling the same things, our initial conditions are the same, so those go away. And now I'm left with B to the 2/7 equals A squared. So I'd get like B to the 1/7 equals A. Does it, you see that? Because I take the square root of both sides and things need to be positive. So that's why I don't need to worry about plus or minus. Did everyone see how I got here? That A equals B to the 1/7. Don't we let that sit for a little bit? I can also write, if I put everything to like the 7th power, I'd get B equals A to the 7th. So we're going to work through a lot of problems about this. That's what this whole section is about. 7 is coming from that there's 7 days in a week. So if I'm doing hourly to minutely, I would need to use 60. But putting either the 1/7 or to the 7th on one of them matters. The way that I like to think about it is the smaller growth factor, so like daily growth factor, that's going to be a smaller growth factor than a weekly. I can't double in a day and then only grow a factor of 1.2 in a week. So my daily growth factor is going to be a smaller factor than my weekly growth factor. Do you guys agree? So to get them to be equivalent to each other, I need to make my smaller growth factor bigger. So I'm raising it to the 7th power. And I get that 7 from there being 7 days in a week. Similarly, to get it, I can need to make b smaller to equal a. So I put b to the 1/7 because roots make things smaller. And this is all working because we're talking about growth and not decay. So things are more than 1. Once we get into things that are less than 1, it gets a little backwards, but we don't have to worry about that. Okay. So either b is going to equal a to the 7th or a is going to equal b to the 1/7. Similarly, those are things that are equivalent. How do you guys feel about what I just said about comparing those growth factors? Are we still a little lost? Or do we want to do a problem and see if we're still lost? Okay. So changing the time period. So a biologist finds a 30-minute growth rate for a certain type of bacteria is 0.85. So 3-minute growth rate, 0.5. So that's a growth rate. So that's not the growth factor, okay? What we did up earlier was comparing growth factors, not growth rates. So I can't use what I did before to talk about rates, but I can use what we talked about as a middleman, all right? So if I'm given that the 30-minute growth rate, let's call that like R of M for like 30 minutes. That's going to be 0.8. What should I do from here to help me find the 1 hour growth rate? What should I do? I only know how to compare factors. So what should I do? Multiply by 2. Why multiply by 2? So when we're talking about exponential growth, things grow exponentially. So in twice as much time, I'm not going to have just twice as much, right? My growth rate is I'm growing 85% in that time. So we're not talking about linear growth, how I'm just like, oh, if I did this in 30 minutes, I'm going to do that same in that 30 minutes. No, that's the difference here. I'm growing in that first 30 minutes, I'm growing 85% of what I started. And then that next 30 minutes, I'm growing 85 of what I was just at that 30 minutes again. So it's not linear growth. I'm shooting up really, really fast. So I only know how to compare factors and I'm given a rate. What should I do with my rate to help me compare to the hourly rate? Laptop's gonna die. If I'm given a rate So wouldn't I just make my rate into, I don't want you guys to tell me the answer. We just talked about comparing factors, but I'm now given a rate. Should I change my rate into a growth factor? Is that something I should do? Should I change my growth rate into a growth factor? Because then I can compare factors. Yes, right? So I want to find A of M. I'm just going to add 1 to my, right? So A, which is going to give me 1.85. So that's my growth factor for my 30-minute. That's my 30-minute growth factor. Okay, so we've talked about how there's 2 30-minute time periods and an hour. So let's call A of H my 1 hour growth factor, right? So how can I compare my 1 hour growth factor to my 30-minute growth factor? I need something either here or something here. Probably something to the raised to the AM since I have that number. What should I put right here to help me find if there's 2 30-minute time periods in 1 hour? I need to make my growth factor bigger. 2, exactly, right? I want to square it. So I'm going to do A to the H is equal to 1.85, because that was my 30-minute factor squared. Yeah, exactly. And that's going to equal, oh, I don't know, 1.85 squared, 3.4225. Okay? Or we can just say 3.4. Doesn't matter. Cool. So that's my 1 hour growth factor. So I'm using all these things that I've learned so far to chain to get to my answer. So I was asked to find the 1 hour growth rate. So have I done that? Have I answered the question? I have found the 1 hour growth factor. That is not the same as the growth rate. So I'm not done. How can I find the 1 hour growth rate now? What can I do given that my 1 hour growth factor is 3.4225? So how can I find that growth rate? Why would I divide by 2, Griffin? Remember the fun little, we learned that A is equal to 1 plus R. That's what we used right here. Similarly, I can use it, rearrange some things, and I get A minus 1 equals R. So I don't want to divide by 2. I'm not going to be doing a lot of multiplication and division unless I'm going to use a lot of exponentials, or I'm going to add 1. Right? So I know that corresponding growth rate and growth factor are off by 1. So if I'm given that the 1 hour growth factor is 3.4225, how can I find the 1 hour growth rate? If I know this right here. Remember, R is our growth rate. So I have a factor right here. So this is A of H, right? You're super close, Abby. Wait, no. So I'm given an A of H. I found out that A of H is 3.4. How do you guys think I can find R of H? Yes. Ronald, you got it. I'm going to take that number and I'm subtract 1 from it. The growth rate is just 1 less than the factor to kind of get rid of that like 100% that we added to get our factor. So I just get 2.4225. And that is my 1 hour growth rate. Okay. So we went from 30-minute growth rate, we call it GR, and then using that A equals 1 plus R, that's how I found my 30-minute growth factor. And that's, then I used, since there's 30 minutes and 1 hour, that gave me my 1 hour growth factor. And then I used this down here to find my 1 hour growth rate. So I had to pull in a lot of things that we've been learning to make all those connections. Okay, so when we're talking about exponential models, if I have 2 time periods, I'm not going to want to multiply by 2. That's going to be like a linear progression. So instead, I'm going to raise it to the second power like we did here. Okay. What do you guys think that was the most difficult part about that problem? Was it going from the 30-minute factor to the 1 hour factor? Yeah, it is a lot of information that's new, which is the reason that we're having class on Thursday, because I don't want to rush through all of this stuff, because I do want to get through all of it and you'll need it in more courses. So, okay. I think we have time to do one more problem and we'll be good. Okay. This one shouldn't be too bad. So we're back to our chinchilla farm, right? So there's 20 chinchillas. After 3 years, there are 128 chinchillas. We already know that, right? Oh, the difference between growth rate and growth factor. Yeah, let's add a page. How do I add a page? So growth rate, let's do growth factor on top actually. So growth factor, we call that A. Growth rate, we call that R, right? So it's a growth factor. It's always going to be greater than 1. A growth rate doesn't necessarily have to be greater than 1, but it's going to be a percentage. And if we're not given it, we can find it by doing R is equal to A minus 1. And if we're not given A explicit, we can find it by doing A is equal to R plus 1. So, and we get A plus 1 because we're given the definition of R to be f of x plus 1 minus f of x is f of x. And then A in our definition, not in our definition, just something we found out, x plus 1 over f of x. Okay, so that's a little quick recap of growth factor and growth rate. Growth factors I can compare for time, straightforward. Growth rates I cannot because of this addition. Okay, or subtraction, whatever. Does that clear that up for everybody? Difference between growth rate and growth factor. Okay, cool. Alrighty. So we're actually just gonna stop here. We're not gonna do that problem because that problem will be a good recap for next time. So let's do our exits up right here. Let me open this. Okay, so the teacher question of the day is going to be if A is the 3-year growth factor and B is the 1-year growth factor, is it true or false that A cubed will equal B? True or false? So you guys don't have to type too much, just true or false. Let me stop recording because we don't need to do that. You're okay, bud.